Now we will see the machine learning revision. So whatever the algorithms that we have studied, we will take up each and every algorithm, and we will understand, we will go through the important mathematical expressions as well as important concepts that are related to each and every algorithm that we have studied, and we will solve some of the important models that are related to each and every algorithm. So if you look at the machine learning algorithms, the broad classification of machine learning algorithms is supervised machine learning and unsupervised machine learning, and we studied the simple linear regression, multiple linear regression, logistic regression in our preliminary machine learning algorithms. And here again, the simple linear regression and multiple linear regression are the regression algorithms. Those are linear regression algorithms, and logistic regression is a binary classification algorithm, right? Similarly, decision trees, k-nearest neighbors algorithm, naive Bayes, support vectors, LDA, linear discriminant analysis, we will study, we have studied all these algorithms under supervised machine learning. And we have the feed forward neural networks also, which is a very preliminary or the fundamental level introduction to the deep learning that is given by the artificial neural networks. So all these algorithms will come under supervised machine learning. And in unsupervised machine learning, we have mainly we have clustering methods. In clustering, we have mainly the top-down approach and bottom-up approach. And again, in every approach, in every method, we have again two types. Divisive as well as hierarchical algorithms are there. So we have studied them, and we will take up and we will revise them thoroughly here. Then the principal component analysis. PCA is another important unsupervised machine learning algorithm. So we will revise that too. And along with these algorithms, here we have the bias variance trade-off as well as the model regularization techniques, where we will study ridge regression and as well as the cross validation methods like k-fold cross validation, leave one out cross validation, etc. And these are mainly used for model generalization purpose. We know that, right? So let us begin our study, our revision with the simple linear regression method. And before going into that, here I will give you a very important table that is related to the properties of each and every algorithm. So what are the basic characteristics of the algorithm, or what is the behavior of the algorithm in terms of eager versus lazy learner, generative versus discriminative nature, and parametric versus non-parametric nature is to be understood for all the algorithms that we have in our syllabus, right? You know, eager versus lazy learner. This is one characteristic where in our syllabus we have only one lazy learner, that is k-nearest neighbors algorithm. Apart from that, all other algorithms are eager learners only. So what is this difference? Eager learner versus lazy learner. In eager learner, whenever you provide the training data, it starts working with the training data and it provides some output based on that training. So it works with the algorithm, works with the training data, and it won't be idle, right? So that is eager learner. Whenever you provide the training data, it works with the training data. The algorithm starts working with the training data. Such type of algorithm is eager learner. And all our algorithms are eager learners except k-nearest neighbors algorithm, right? Lazy learner, that is a lazy learner will hold the data. that is the training data you will provide. You just provide the training data set and it just holds the training data and it won't do anything with the training data until you provide some test set example, right? For that, k nearest neighbors is a good example. So k nearest neighbors is a lazy learner. And if you observe, all remaining algorithms are eager learners only. Next classification, that is generative versus discriminative characteristics. Among all the algorithms, we have only one generative algorithm in our syllabus, and this generative and discriminative nature is applicable only to supervised machine learning techniques, and it is not applicable to unsupervised machine learning techniques. That's why I have mentioned it as a neither. It is neither generative nor discriminative. Your unsupervised machine learning techniques are neither generative nor discriminative, and this classification is applicable only for supervised ML algorithms. So here in generative as well as discriminative classification, only naive Bayes algorithm is generative, and the remaining algorithms are discriminative only. So naive Bayes is the algorithm which is generative, and the remaining algorithms are discriminative. And of course, a linear discriminant analysis is also it can be considered as a generative algorithm, but an important algorithm that we consider as generative algorithm is naive Bayes only. Okay, so the discriminative nature, it takes the probabilities and it takes the input features and it gives the output probabilities. But in generative algorithm, it from the labeled data information, from the target information, it calculates the prior probabilities, and those prior probabilities can be considered as the generation of new data examples. That's why the naive Bayes algorithm is considered as a generative algorithm. And another important characteristic is parametric versus non-parametric classification. Here we will go algorithm by algorithm. And linear regression includes simple linear regression, multiple linear regression, as well as ridge regression. Even polynomial regression is also a part of multiple linear regression. And in all those regression methods, we will have the model parameters. Right, the W0 is the bias, W1, W2, W3 associated with every feature. We have one weight, and that weights along with bias are considered as the model parameters, such that linear regression is parametric and logistic regression is an extension of linear regression. Right, but whatever the model parameters that we have in linear regression, in logistic regression also we will have the same model parameters which will describe the weighted summation of features with the bias, such that it is also parametric. And decision trees are non-parametric models. You don't have any parameters, as well as here we have no assumptions about the data in non-parametric models. So decision trees are non-parametric, as well as in k nearest neighbors algorithm also you don't have any assumptions about the relation between your features and the target. How can we define parametric and non-parametric? If there is an assumption, a defined assumption between your features and target, that assumption gives you the model parameters. So in such a manner, we have an assumption, we have a defined assumption in linear regression, logistic regression, as well as in naive Bayes algorithms, and we have the model parameters in those algorithms. So in k-nearest neighbors algorithm as well as in decision trees, we don't have any such kind of assumptions. They are non-parametric. Right. Similarly, naive Bayes is parametric because whatever the probabilities that we calculate, the class conditional probabilities that we calculate in naive Bayes are the model parameters. So if we are having model parameters, they are trainable model parameters. Right. So you will get those model parameters are trained until we get an optimized model. Right. So that is the idea in regression, and the idea in naive Bayes is slightly different. So we calculate the class conditional probabilities from the frequency tables, from which we will get the product of class conditional probabilities, which gives you the posterior probability values. Among them, from that, the maximum likelihood approach. This approach is called maximum likelihood approach, and the maximum value of the product of class conditional probabilities gives you the prediction. That is the idea of your naive Bayes algorithm, such that the class conditional probabilities are the trainable parameters in naive Bayes. And support vector machines. Support vector machines are non-parametric. Right. The reason here is we have only a certain set of data examples, certain set of data examples based on which the entire prediction will be obtained. Your class prediction is obtained, or it is based on only a few feature vectors given by a very few data examples. Feature vector is nothing but, feature vector is a representative of the data example. Okay, so because if you change the data set, there is a chance for a change in those support vectors. If you look at the remaining parametric algorithms in the linear regression, or whether it is logistic regression, or if it is a naive Bayes algorithm, let us say I am having a data set with 100 data examples, and I have a data set with 100 data examples, and I am increasing the data set from 100 to 1000 data examples. Okay, the number of model parameters will not be adjusted, or it will not be changed by that, but the number of support vectors will change if you change your data set. So that's why, so if you change the data set size, if you adjust the data set size, if the number of model parameters are changing, then that will be a non-parametric model. So irrespective of the number of data examples in your data set, you must have same number of model parameters. Then only that model is considered as a parametric model. But it is not the case with support vector machines. In support vector machines, what happens is, if you adjust the data set size, the number of support vectors gets changed. They will get change. There will be, there is a chance for the change in the support vectors. such that the algorithm is a non-parametric algorithm. And linear discriminant analysis, we have that is considered as parametric, and all artificial neural networks are considered as parametric model only. Whatever the weights as well as the bias that we obtain for each and every neuron will be considered as one parameter here. And clustering is non-parametric, because just we will do some grouping in clustering, so that's why it is considered as non-parametric, and principal component analysis is parametric. So this is a very important table. So this is a very important table, and in GATE 2024 there is a 1 mark question that is related, that is based on this question, on this analysis: principal component analysis, naive Bayes classification, and logistic regression. Principal component analysis, PCA, is a dimensionality reduction technique, right? LDA and PCA both are dimensionality reduction techniques, we know that. So PCA is dimensionality reduction technique. And logistic regression is discriminative. Logistic regression is discriminative. PCA is dimensionality reduction technique, and naive Bayes algorithm is the generative model, right? So this is the simple characteristics or behavior of that specific algorithm. So you may expect this kind of simple 1 mark question in GATE paper. Right now, if you look at the characteristics, this practice question, select the characteristics that describe the support vector machine algorithm. It is an eager learner or lazy learner, whether it is a generative model or a non-parametric model. And support vector machine is a eager learner, right? Because it works on the training data set to figure out what are the support vectors that are nearer to the obtained decision boundary. So based on which the decision boundary gets adjusted in an optimized manner. So it is an eager learner, but not a lazy learner. And it is not a generative model. Naive Bayes is a generative model, LDA is generative, and it is a non-parametric model. Support vector machines, SVM, is non-parametric in nature. The explanation that the reasoning for its non-parametric behavior just now I have explained. If I am having 100 data examples, for suppose, let us say among those 100 data examples, 5 support vectors we have. 5 support vectors. And if I change this from 100 data examples to 1000 data examples, then these 5 support vectors will be changed to just 3 support vectors, or they may be increased to 7 support vectors, such that these support vectors will not be considered as trainable parameters. Support vectors are not considered as model parameters. Remember, support vectors are nothing but data examples. The support vectors are not model parameters. This is very important point. a very important point in support vectors missions algorithm is support vectors are not model parameters. That's why this is a non-parametric model or non-parametric algorithm. So you again go through the table that I have given to you, and that will be helpful for you in answering these kind of questions. Okay, right. Now we will begin our revision of the first algorithm, that is a simple linear regression. And in machine learning mainly we have supervised machine learning algorithms and unsupervised machine learning algorithms. And in supervised machine learning algorithm, again we have regression as well as classification. Regression means, and this classification, that is the regression as well as classification, that binary classification or multi-class classification, that this separation is based on the target that is there in your labeled data set. You know what is labeled data set and what is unlabeled data set. In supervised machine learning algorithms, we will use only labeled data set. That means the data set comprises of the inputs as well as the output. And inputs are called features or predictors, and output is called the target, or sometimes it is called ground truth, right? So in simple linear regression, simple linear regression is the basic idea which is related to the regression algorithms, and this is not for practical implementation. This is only for mathematical understanding. Simple linear regression is a stepping stone to understand the multiple linear regression, as well as a very important classification technique, that is logistic regression also. And even for generalization, the ideas of ridge regression and lasso regression, everything is directly connected to or linked with the simple linear regression algorithm. So understanding the math behind the simple linear regression is very much important to understand the algorithms like multiple linear regression models, as well as the ridge regression, polynomial regression, and even logistic regression also, right? This is not for practical implementation, because it is not possible to do wonders with just one feature. But how we can generalize this idea to a data set with n number of features can be understood, and you can do that, or you can extend this idea to n number of features once you have a complete picture of simple linear regression. And in last year paper, we don't have any questions related to simple linear regression or multiple linear regression or even logistic regression too. This year we can expect at least 2 questions. This is what I am expecting from the ideas of regression. Okay, and these are basically statistical methods. All the regression techniques are statistical methods, right? So in simple linear regression, as you know, we have only one feature and we have one target, and we will have, or we assume, a linear relationship between this feature and the target. If that assumption is if you are not considering that assumption, then the algorithm is not applicable. If there is a non-linear relationship between your input variable and the output, then simple linear regression is not applicable there, right? So here we start the algorithm, the study of the algorithm with an assumption that yes, there is a linear relationship between your input and output. Just like how there is a linear relationship between stress and strain, velocity and distance, that could be either directly proportional relationship or inversely proportional relationship. How that relation proportionality is existing between the input or the independent variable and the output and the dependent variable, then only we will consider that data for simple linear regression. So, your feature x and your target y are said to be having a linear relationship between them. Okay, right. So, as I mentioned, it is a supervised machine learning model in which we have one dependent variable which varies linearly with one or more than one independent variables, that is linear regression. This is a generalized way of explaining the linear regression. We have one or more than one independent variables. Independent variables are nothing but features or predictors, and the dependent variable is target. Right. So, if you strictly confine yourself to the one independent variable, then that is considered as a simple linear regression. Right. Now, if you consider the data set, here I am giving you the generalized way of representing a data set, which is applicable to multiple number of features. If I am considering x1, x2, x3, so on up to xn. Okay. So, what are these x1, x2, x3, xn? These are the features. Okay. So, these are considered as features. And if I am taking a I here, then this represents the feature vector of ith data example. This is given as the feature vector of ith data example. Right. So, that means if I am taking the first data example, first data point, that would be given as x11, x12, x13, so on up to x1n, and that is the first data example corresponding feature vector, and the data set would be, and now I am representing it with the vector x of a specific data example I. So, here I am taking this xi vector, and corresponding with that there will be a target for that specific ith data example. So, that would be given as a yi, and in general this I ranges from 1 to m. That means we are having m number of data examples. We are having m number of data examples. right? So this is the generalized representation of a labeled data set. Any labeled data set can be represented like this. I have one vector, one feature vector associated with every data example. Those are nothing but the values of each and every feature, right? So if I am having 3 features, in the first feature corresponding value is 3, second feature corresponding value is 17, third feature corresponding value is 5. So 3, 17, 5 is the first feature vector of your first data example. And for this 5, 14 and 7, whatever the values that we have taken, associated with it there is a target value, right? So that defines for all data examples ranging from 1 to m, that defines your data set. So this is a generalized way of representing any labeled data set. So this is the generalized way of representing labeled data set. I don't have this. I am having only the feature vectors. Then it becomes an unlabeled data set, right? So now similarly, I don't have all these x2, x3, x4 up to xn values. I am having only x1. I am having only x1 in this feature vector. Then this data set corresponds to the simple linear regression. Of course, the assumption is there is a linear relationship between this x1 and the y. Okay, right. So in simple linear regression, as I mentioned, we have only one independent variable and one dependent variable, right? An independent variable is input and the dependent variable is the output, and you have to predict the dependent variable always based on the given independent variable. And in simple linear regression, the model is a best fit straight line which describes the relation between input and output, right? So here I am having x as my input and y as my output, and the relation between x and y, the assumed relationship between x and y is a proportional relationship, right? This is x proportional to y or y is proportional to x, and with an appropriate slope as well as intercept, if you consider the relation, that would be given as y is equal to mx plus c. This y is equal to mx plus c expression describes the model in simple linear regression, right? So the model is a straight line with some slope and intercept, and here rather than m and c, we will use y is equal to beta naught plus beta 1 x, or y is equal to w naught plus w1 x as our model representation. The model can be represented like this, and here w naught and w1 or beta naught and beta 1, they are called model parameters or coefficients, and w1 is a weight and w naught is the bias. So here in this representation, w1 is the weight and W naught is the bias. Right. So if you consider the generalized data set, I am not going to the house price prediction example and all, as I explained in our regular class. Just I am showing one data table where I am having the feature X, and I am having the target Y, and there is an assumed linear relationship between this X and Y. So you just see, this is one data example, this is another data example. Like that, I am having 41 data examples such that the value of M is equal to 41 here. So this is the generalized way of representing this kind of data table, where in the feature vector I am having only one value. Every vector contains only one value, one input value, and your target is to be considered as a one value related vector. But of course, it is not meaningful here in simple linear regression, but as going forward in multiple linear regression and polynomial regression, this kind of vector representations and its extension to matrix form is very much needed for us, right? Right. So now another important plot that is required for us in simple linear regression is scatter plot, right? So this is a scatter plot. So what is the scatter plot? This is another way of representing the data table. All the 41 data examples, whatever we have in the data table, they have been given here like this. This is your X, that is your independent variable, and this is your Y, that is your dependent variable. So scatter plot is another way of representing the data, that is the data table, right? So every point here represents a single data example, right? So every point here represents a single data example. Right? Now we will see the model generalized expression. I already have mentioned that the generalized expression for the model would be given as a straight line. So the generalized expression for the model is given by a straight line. Right. So that would be given as. Now I am considering it a more appropriate way. The y hat gives us the model, and that is given as y hat is given as the bias W naught plus the W1 xi, such that this is a function of the input. This would be considered as the generalized way of representing a model. A model is nothing but a predicted value, that the model gives you the predicted value, and this expression for your y hat that has been taken for an ith data example would be given by this expression. Your y hat of I is equal to W naught plus W1 xi, right? Now how to define the bias as well as the weight. So this is W naught is bias and this W1 is the weight, and here I am just showing you a straight line. I am drawing a straight line, some straight line which is passing through the data examples, right. So this is a model, right, and how do we get the prediction for one data example? Suppose let us consider this data example. I am taking this data example, and this data example is having an x value that is equal to 1750, right. And its actual output value is equal to 25. But if you project this onto this model line, it is predicting that value as 29, right. So for every x, there is one predicted value that has been given by this straight line, right. So finding the best possible straight line is nothing but getting the best fit model, right. So what is the objective of simple linear regression? Finding the best fit straight line, right. So the idea is simple. So the objective of simple linear regression is finding that best fit line. Now how to define this bias as well as the weight? Independent of the features that are there in your model, and this bias definition is valid for multiple linear regression also. And independent of the feature or the features that are there in your data set, if there is some non-zero defined target value for a specific data example, that would be given as a bias. Independent of the features, the possible value of the target is bias. That would always be given by y-intercept. For a y-intercept value, see here, if I am extending this back, this is the y-intercept value, and at x is equal to 0. What do you mean by this? My feature value is 0, and if my feature value is 0, the output value is equals to 3, right. So how to define bias? Independent of the features, or if all the features are 0, then the possible value of the target is bias. And how to define weight? For a unit change in your predictor or your feature, I am changing the feature value from 4 to 5 or 17.5 to 18.5. Just I am changing it by 1 unit. The proportionate change in the output for 1 unit change in the predictor or the feature, the proportionate change in the target is given by the weight. So for a unit change in a feature, the change in the target, the proportionate change in the target is given as the weight. Okay, so these are the basic definitions of bias as well as the weight, which are called as the coefficients or the model parameters, right. The linear regression block diagram, and this block diagram is equally applicable for multiple linear regression also, right. So we have the input training data, and because we are discussing simple linear regression, I am considering the input training data as x comma y I am defining it as x comma y or xi comma yi for I ranging from 1 to m. Okay. So this is nothing but either this, the scatter plot, or this kind of data table with one column that describes the feature and another column that describes the target. Now, in this input training data, which is a labeled data, the input will be given to the model. What this model will do at the time of initialization, based on the assumption, the linear assumption that you have, it gives you some arbitrary model. Okay, this is not your final model, this is just your first model or initial model, which is always an arbitrary model. Because you are assuming a linear relationship between your input and output, this model gives you some values of W0 and W1. Okay, let us say it is giving W0 is equal to 3 and W1 is equal to 5. Then what is the model that you are obtaining from this? That model would be given as y hat is equal to 3 plus 5x. For every data example, you need to calculate the predictions. Right. Suppose, what is this 3 plus 5xi? 3 plus 5xi is this straight line, right, with an intercept 3 and slope 5. Right. So, is it your final model? No. This is your initial model, and in regression, the initial models are arbitrary models. Okay. We will choose some random values of weights, and with that weights we will get the model. Okay. So that is your initial model. Right. Now, for each and every data example that is there in your training data, with these given model parameters, you need to calculate the output. And that output, that predicted output is given as y hat I. And in the training data, already you have yi because it is labeled data. Right. Now, calculate the error function. If it is error, that is just the difference between the prediction and target. The absolute difference between the target and the prediction is nothing but the error. But here in simple linear regression, we will always go with a cost function. Here we will go with loss and cost. There is a slight, a small difference between loss and cost. If you take the error for a single data example, that would be considered as loss, and the cumulative loss is the cost. Right? The cumulative loss. That means if you consider the loss for each and every data example, and if you get the summation, then that gives you the cost. Right? Loss is the error calculated for a single data example. And in literature, there are so many error functions. But here in simple linear regression, the most widely used error function is mean squared error function, right. So, for one data example, there is simply the difference between yi and y hat I whole square. Because we have to take that as a cost function, you need to take the summation, the accumulation with the mean. So, that is why the cost function, whatever we have here, that would be given as 1 by 2m, and we know why we are taking this 2 and why we are taking the mean value rather than just the cumulative sum. Summation I is equal to 1 to m yi minus y hat I, or y hat I can also be given as f of xi. Whole square. So, the mean squared error, and this error, whatever the difference that we have here, that error is also called residual. This is also called residual, right. Now, the mean squared error function j, whatever I have here, that is a single value representative of your model. Am I correct? So, what this j is representing, if this is a very far from the actual best fit model, this error would be a very large value, right. So, you have to decrease that error by some means. So, if I am able to reduce this j, that is your cost function. J is what? J is the cost function that is used in simple linear regression. So, this is the cost function that is used in regression. In multiple linear regression also we will use the similar kind of expression, just instead of one weight, we have multiple weights, multiple weighted summation of the features will be there in that expression. Okay, in multiple linear regression I will give you the expression. Okay, now we are getting the cost function j here, and this j depends on W naught and W1 that is the model parameters. Cost function is a function of model parameters, and there is an optimization technique, and the most widely used optimization technique is the gradient descent algorithm. And by using the optimization technique like gradient descent, we will make an attempt, or we will try to reduce the cost function. The cost function is to be reduced. For that, we will use some optimization method. The most widely used optimization method is the gradient descent algorithm. Okay, so if I am, let us say I am having 25,000 as my error in a problem, I have 25,000 as my cost function value, and on applying some optimization method that has been decreased to, it is giving the optimization method works on the model parameters and it adjusts the model parameters. This W naught and W1 gets adjusted by the optimization technique or optimization algorithm, and such that you will get a new set of W naught and W1 to the model from this optimization technique. Got the idea? So, here everything is done with respect to the model parameters W0 and W1. So, here W0 and W1 gets adjusted in a way to decrease the cost function. So, this W0 is changed from 3 to 5.5, W1 is changed from 5 to 4.9, such that again you will get a straight line, and for that straight line if you calculate again y hat of I and if you calculate the cost function, your 25,000 would be reduced to 14,000, right. Again it is an iterative process. Usually an iterative algorithm will be used for optimization, and the most popular algorithm is the gradient descent only. In linear regression, simple multiple linear regression, logistic regression and artificial neural networks, we will use gradient descent algorithm only. Okay. So, this is the block diagram of the simple linear regression. So, you have to go in an iterative manner until there is no change in the cost function j. Ideally, it has to be reduced to 0. The error is to be reduced to 0, but that is not possible practically, right. So, you have to reduce it to a certain possible extent, to the certain possible extent. So, just whatever the model that I have shown there, just that block diagram has been represented here. You have the training set where we have a features and target, and the learning algorithm. What is the learning algorithm? That gives the model parameters. During the initialization, the learning algorithm gives some random values, and the hypothesis function is nothing but the straight line, because it is simple linear regression model. So, you have to provide input to the hypothesis. These are the inputs of your data table, such that it provides your prediction or the estimation, right.